Hi everyone, dear students. We are studying our mathematics paper 1, linear algebra, and this is our lecture number 4 on unit number 1. In this lecture, we are going to see Gauss-Jordan method. In previous lecture, we have seen Gauss elimination method for solving system of linear equation. Now we are going to see Gauss-Jordan method. So for that method, we'll see what is reduced row echelon form. So a matrix is said to be in reduced row echelon form if the following condition hold. So here first, as like in row echelon form, if there are any row which consists of entirely zero, then they are placed together at the bottom of matrix. So second condition, for first non-zero entry of each row is 1. This is called as a leading 1. In any two successive rows that do not consist of entirely 0, leading 1 of lower row must appear to the leading 1 of upper row. So this is similar to row echelon form. And the fourth condition is different. Each column that contains leading 1 has zeros elsewhere, and this is the important condition for reduced row echelon form. So the column which contains leading 1 means first non-zero entry, and if you are saying that it is 1, then it is leading 1, otherwise you can call this as a leading entry. So in that column you must have zeros everywhere else. In other words, echelon form of a matrix is said to be reduced row echelon form if first non-zero entry of each row is 1 and each column that contains leading 1 has zeros elsewhere. Means if you have given a matrix and you are asked to reduce given matrix into reduced row echelon form. So first reduce that matrix to echelon form, and then these two conditions you have to apply. First non-zero entry of each row is 1, and second is each column that contains leading 1 has zeros everywhere else. And if reduced row echelon form is obtained, again count the total number of non-zero rows. That gives you the rank of given matrix. And using this reduced row echelon form, you can solve the system of linear equation, and this method is called Gauss-Jordan method. So if augmented matrix is reduced to its reduced row echelon form, then we write the corresponding system and solve it by back substitution, and this method is called Gauss-Jordan method. So remember, for Gauss elimination method, your augmented matrix is reduced to row echelon form only, and for Gauss-Jordan method, your augmented matrix is reduced to reduced row echelon form. Let us see an example. Solve the following system of linear equation by using Gauss-Jordan method. So three equations in three unknowns are given. First equation is 2x plus 3y minus z equal to 2. X plus 2y plus z equal to minus 1, and third equation is 2x plus y minus 6z equal to 4. So here is first matrix form of given system. So collect the coefficient matrix of variables, and RHS constant. Now next step is augmented matrix. So join RHS constant to coefficient matrix. Now reduce this matrix to reduced row echelon form. So here first we want leading 1, so apply R1 2. So that will reduce this matrix to matrix having first row as 1 2 1 minus 1, second row 2 3 minus 1 2, and third row is 2 1 minus 6 4. Now to reduce this matrix, so we want all entries below this leading 1 or leading entry are equal to 0. So apply R2 minus 2R1 and R3 minus 2R1. So your matrix will be equivalent to this matrix. So perform this calculation in second and third row. Again, go to the second row. So make this entry is equal to 1. So you can take minus sign common. So apply minus R2. So you will get, or you can divide by minus 1. So your R2 row will change to 0, 1, 3, minus 4. Now this is our leading entry of second row. Now we want 0 below that leading 1. So apply R3 plus 3 times R2, and simultaneously I want this entry equal to 0 because the second in the second row we have leading 1, and to reduce in reduced row echelon form, which a column which contains 1, we want zeros everywhere else, and for this entry to be 0 we have to apply R1 minus 2 times R2. So you will get this 1 0. Now this R1 will change, but remember this 0 will not change, and this second condition hold. Now go to the first leading entry of third row. Now this is already 1, so this is leading 1 of third row. Now what we want in this column, we want this entry equal to 0 and this entry equal to 0. But to make this entry equal to 0, you have to use this R3 row only. Don't use R1 and R2, because if you use R1 and R2 row, so this 0 may be disturbed. So we have to take care of zeros that we have already obtained. So we are using R3 row only. So to make this entry 0, so apply R1 plus 5 times R3 and R2 minus 3 times R3. So remember why we have made here 0, because we have to identify first leading entry of each row. So for first row, first leading entry of 1, and in that column we want zeros. So here already we have zeros. Now go to the second leading entry of second row. So here is this 1, and we want in that second column zeros elsewhere. Again for third row, this is your leading 1, and in that column we want zeros everywhere except this entry, and therefore we are making this entry equal to 0 and this entry equal to 0 by applying this transformation. So your matrix will reduce to this matrix. Now there is no question about this minus 6, because minus 6 is not a leading 1. So we just have to identify the column which contains leading 1. So first column contains leading 1, and therefore in that column except this entry we want zeros everywhere. For second column leading 1 is here, and we want except this entry zeros everywhere. For third column leading 1 is here, so except that entry we want zeros everywhere. And now this matrix is in reduced row echelon form. So count the total number of non-zero rows. So there are total 3 non-zero rows. If you hide this last column, then rank of coefficient matrix is also 3. So here common rank is equal to 3, and which is equal to number of variables, and therefore given system has unique solution. How to obtain this solution? From last matrix we can rewrite system. So let us see last matrix. So from this only one variable is there, x, coefficient of x is 1, then coefficient of y is 0, z is 0. So directly you will get x equal to minus 23, y equal to 14, and z equal to minus 6. So this is the solution of given system of linear equation, and we have directly got the solution in Gauss-Jordan method. So this is easier method as compared to Gauss elimination method, but here we require more number of elementary transformation. So These are some examples for your practice. So you can apply Gauss-Jordan method to solve the system, and you can check whether your answer is equal to this answer or not. Again, second homogeneous system is there. Again, apply Gauss-Jordan method. So for Gauss-Jordan method, your matrix is reduced row echelon form. So this is about Gauss-Jordan method, and here we have completed our unit number 1, matrices and system of linear equation. Next, we will see definition and examples of vector spaces. Let us stop here.